This section is 8.2.1. How can I rewrite it? Exponents and scientific notation. The learning target for this section is I can simplify expressions with positive exponents, and I can write large numbers in scientific notation. So at the end of this lesson, you should be able to say this. I'm going to start with a review of what exponents are. Exponents have a base, and then they have an exponent. So in this case, the base is a 2, the exponent is a 4. What this means is the 2 is multiplied times itself 4 times. So the base is the number being multiplied. The exponent tells you how many times that base is multiplied times itself. In this example, 2 to the 4th power, that is equal to 2 times 2 times 2 times 2, and that is equal to 16. It's 2 multiplied by itself 4 times. Now that we've had that review of exponents, you're ready to start this chapter or this section. We'll start with the first problem, which is 8-36. Is 3 to the 5th power the same as 3 times 5? Put me on pause and work on that for a few minutes, and rejoin me in a minute. All right, you've had a chance to work on this problem yourself. Is 3 to the 5th power the same as 3 times 5, or we could also express it as 5 times 3. 3 to the 5th power can be factored out this way. So 3 to the 5th power is equal to 3 times 3 times 3 times 3 times 3. We're multiplying 3 times itself 5 times. Well, I'm not going to say what that's equal to yet. If we look at 3 times 5, or 5 times 3, that is 3 plus 3 plus 3 plus 3 plus 3, 5 times. Just looking at these two, you can see that the two of them are very different. 3 to the 5th power is 3 multiplied times itself 5 times. 3 times 5 is 3 added together 5 times. So that's our explanation as to why they're different. 3 to the 5th power is 3 multiplied 5 times. 3 times 5 is 3 added 5 times. And that makes a big difference, because if we figured out what these are on the calculator, 3 times 3 is 9. If we multiply it one more times by itself, that's 27. If we do one more time, that would be 4 times, it's 81. And then if we multiply 3 times itself 5 times, we get 243. But what do we get if we add 3 together 5 times? We get 15. So 15 and 243 are very different numbers. All right, let's move on to the next problem. In this problem, you are going to look at the original form of an expression with exponents, and then you're going to factor it out, and then you're going to figure out what the simplified form of that is. Work on these by yourself for a few minutes and then and put me on pause, and then I'll rejoin you. All right, you've tried these problems yourself, so why don't you compare your answers to mine as I work through these problems. 2 to the second power, that's 2 times 2. 2 times itself twice. And then 2 times itself 4 times looks like this. And if we count up the 2's, 1, 2, 3, 4, 5, 6, we get 2 to the 6th power. Moving on to the next one, 3 to the 7th power times 3 to the 2nd power. 3 times itself 7 times. One, two, three, four, five. Okay. 3 times itself 2 times. And then if we add them all up, we get 3 to the 9th power. X to the 3rd power ends up looking like this. 3 x's multiplied times itself. And then we'll multiply that times x to the 5th power. One, two, three, four, 5, 6, 7, 8 x's. X multiplied times itself 8 times, x to the 8th power. This one, x to the 3rd power is x multiplied times itself 3 times. And then y times itself twice, y to the 2nd power. This one might have been a little tricky for you. Some people think that the xy is multiplied times itself twice, but that's not what's happening here. First, it's x times y to the 2nd power. So we only have one x times y to the 2nd power is y times itself twice. Now if we count that up, 1, 2, 3, 4, x to the 4th power, and y 4 times itself. Okay, y times itself 4 times. All right, let's look at this next one. 7 to the 2nd power, 7 times 7. And that's multiplied times x to the 3rd power, x 3 times. And then we just have one plain old 7 by itself times x to the 2nd power, x times x. If we count up the 7's, 1, 2, 3, there are 3 7's. So that would be 7 to the 3rd power, and 1, 2, 3, 4, 5, x to the 5th power. Now usually when we simplify exponents, we don't leave numbers in that form. Usually what we do is we go ahead and multiply those 7's together and figure out what they are. So 7, I enter that first, and now I'm going to use this function. Let me zero in on that a little. I'm using this function on the calculator, which is x to the y power. So I've entered in the x already, and now I choose that function. You'll notice it turns a light gray color, and now I can put in what the y is. And in this case, the y is 3. So when I say equals, I get what 7 to the 3rd power is, and that's 343. 343 times x to the 5th power. So that's the real simplified form for that. Okay. Now let's do the last one. 2 times x to the 4th power. So I've written out my 4 x's, times 3, and that's just plain old 3 by itself, times x. And again, remember, the 2nd power only applies to the y. So we've only got one x there. And then y to the second power. Y times y. All right. Well, we only have 1, 2, and 1, 3. So we'll just multiply those two together and get 6. And then for x's, we've got 1, 2, 3, 4, 5 of them. So it's x to the 5th power. And we've got only 2 y's, y to the 2nd power. Okay, so we're done. You can compare answers with me. And then I'd like you to do the next problem, which is taking the original form and comparing it to the simplified exponent form. And when you're making that comparison, they want you to look at the base and the exponent of the original form and also of the simplified form. So after you've done comparing those two, write a statement to describe the relationship that you see between those two. Put me on pause and work on that for a few minutes. All right, you've had a chance to look at the original form and the simplified form and compare these two. And probably what happened when you did that is that you noticed that the bases would stay the same, but the exponents, 2 and 5, when you're multiplying these exponents, the exponents themselves can just be added up. So 5 to the 2nd power and 5 to the 5th power, we add 2 and 5, and that becomes 5 to the 7th power. And down here, 2 to the 2nd power times 2 to the 4th power, you factor it all out, it turns out that 2 and 4 are equal to 6. Same thing here. The base is the same. It's 3. So 7 and 2 can be added together to make 9. Here, the base is the same. So 3 and 5 can be added together to make 8. Now, when you get to this, you have to look at the x's separately from the y's. So the bases, when the bases are different, you have to separate out how you add the exponents. So if we have x to the 3rd power and x to the, well, if it doesn't have an exponent, we know it's just x. X multiplied by itself one time is x to the 1st power. So 3 plus 1 is 4. Y to the 2nd power, y to the 2nd power, 2 and 2 is equal to 4. Here, we look at the 7s. We realize 7s to the 2nd power and 7 by itself. That's like 7 to the 1st power. 2 and 1 add up to 3. X to the 3rd power, x to the 2nd power. 3 and 2 add up to 5. Here, 2 and 3 don't have exponents, so we treat them the way we would treat any two numbers that we multiply together. We just multiply them together and get 6. But when we look at the exponents, x to the 4th power, and we've got 1x here, so that's a 1 exponent. 4 and 1 is equal to 5. And there are no other parts of this that have y as a base, and so it's just y to the 2nd power, the same way it is over here. So you noticed all of those patterns. So if you were to write a statement, you would say, when multiplying, exponents, if the base is the same, then add the exponents. So that statement captures the relationship between these two. Now you should work on B. So visualize how you would expand 20 to the 12th power and 20 to the 51st power. Now, when they say expand, they mean factor. So that's the same thing that we did up here, the factored form. So you're thinking about, what does 20 to the 12th power look like if it's factored? That's what expand means. All right, work on that for a few moments by yourself, and then come back to me after that. All right, so you probably thought to yourself, 20 to the 12th power. That's going to be a lot of 20s. I don't want to write them out. I know it's going to look something like this, and then it's just going to keep going. And so they're inside of those parentheses. I know that 20 will be multiplied by itself 12 times. And then 20 to the 51st power, same thing. It's going to be so big that I couldn't possibly write it out. So 20 will be multiplied 51 times. If I added up all those 20s to see how many 20s were multiplied times each other, it would be 12 plus 51, because I would combine those two. That would be a total of 20 times itself, 63 times. So that becomes 20 to the 63rd power. All right, take a look at this last problem. One study team rewrote the expression 10 to the 3rd power times 5 to the 4th power as 50 to the 7th power. Is that correct? Explain your reasoning why it is correct or why it isn't correct, and come back to me in a minute. All right, you took a look at this and you probably thought to yourself right away, the base for this exponent is 10. The base for this exponent is 5. So we cannot just multiply these bases. They're exponents, and so it's a little more complicated. And we can't just add together the two exponents because they have completely different bases. So if you thought that, you were absolutely correct. In fact, we have a little expression that we like to use when we're talking about exponents. We have all kinds of laws, but when in doubt, factor it out. So in this case, if we factored that out, 10 to the 3rd power, 10 times 10 times 10, and 5 to the 4th power, 5 times 5 times 5 times 5. What would we get if we actually multiplied those out? And would it be equal to 50 to the 7th power? 10 times 10 is 100. 10 times 100 is 1,000. So that's what that is. 5 times 5 is 25. 5 times 25 is 125. And 5 times 125 is 625. If we multiply those two numbers together, we would get 625,000, which seems like a pretty big number. But is it the same as 50 to the 7th power? Well, if we do that problem, let's see, 50, so there's our base, and now we'll use this function right here, x to the y power. And now we'll put the y in. which is 7. That's equal to, wow, that is a much bigger number. That is so much bigger than 625,000. That is into the billions. So these two numbers are not the same thing.